Hello everybody. This week we are going to continue our conversation of thermodynamic cycles, and we are going to discuss processes and some of the related vocabulary. We'll talk about various calculation methods needed when you're doing the analysis of this type of processes. We'll focus on air standard analysis of an existing combined cycle plant. We talked about open systems, closed systems, open loop, closed loop, all of that. We have talked a little bit about the first law of thermo, which is all about that energy balance, which is that the sum of total heat must equal the sum of total work. And we are going to expand upon that a little bit more this week, and we are going to discuss ideal versus real processes, like we saw with our diesel cycle a couple of weeks ago. So again, remember, a closed system means you basically have a defined space for your process or your set of processes, like a bubble around them. So this cycle here has a controlled mass for the system you have defined. So really, for a closed system, what is important is whatever you define as your system, the mass when you go from state 1 to state 2 should be the same, right? It remains unchanged. For example, when you go through your combustion process in the diesel cycle, you got an amount of fuel in here, plus you get an amount of air in here, and that's basically combustion and expansion, right? So when we go through that expansion, as the mass inside of this actually changed when we are doing expansion? No, because we are not exhausting yet, right? So the mass inside of the system is still going to be the same as the fuel and the air we originally put in the engine. So that means that mass flow wise, when you actually do the exhaust, whatever the mass of the air and the mass of the fuel you have coming into the engine, you should have the same mass flow of the exhaust coming out, just like we saw during that Excel analysis, right? Now, let's expand upon that first law, looking at a closed system. So there are a series of potato-shaped areas that you can see here. Well, here, this is the system as at its initial state T1, P1, V1, U1. Do you remember what that U is? U is defined as the internal energy of a thermodynamic system. It is the sum of all the energy held by the molecules. It is a measure of the energy within the system. And actually, U measures the gains and losses of energy of the system that are due to changes in its initial state. So back on the system here, it goes from that initial state to that final state, T2, P2, V2, U2. And that is called a process. And during that process, there is some exchange of heat in, out, and some production work in and out. So when you expand upon that first law, really it should be when this system goes through some process where we have some exchange of heat, and we have again heat in, heat out, work in, work out. So when you look at the formula, the difference of heat transferred to the system and work in, work out of the system is the energy change of the system, U. It's really this change of energy, U, that's going to be responsible for going from this point, T1, P1, B1, U1 to that point, T2, P2, V2, U2. V2, I'm sorry, T2, P2, V2. Okay, so that was control mass that we were talking about before, right? So now let's talk let's talk about control volume a little bit. So control volume basically just means that you have a set defined space here. The volume of that space really is not changing during the process. It remains constant. But so it's kind of like where we actually are doing the combustion from 2 to 3 on that diesel cycle, right? You remember? From 2 to 3. You've got a momentary non-changing volume, remember? So what you're doing here, you're putting product in and air coming in, fuel in, and you get some product out. Right? So we put fuel and air as input and we get combustion. The size of the box here doesn't really change and we get some exhaust products out. So we really can treat this as a black box where we put some stuff in and get some stuff out. Right? So that's kind of an important thing about control volume. It's basically just something you put stuff in and get stuff out. But that volume inside here remains constant, so there is no real delta V. Oops, okay. Okay, so how do we deal with that first law for control volume? We still have this heat in and work out of the system, but we can expand that U, that's U here, we can expand that U, internal energy, in terms of all of your first law energy types, right? Hopefully this looks a little familiar from fluid power, I hope. So here is your kinetic energy, your potential energy here, and your pressure work here. So the only addition here is this internal energy. But if you remember back from thermo, we can simplify this a little bit. And realize that enthalpy, or H, is just internal energy, or the specific internal energy, plus PV, right? So if we recall that, so pressure times the volume for each individual state. So if we were to simplify this a little bit, we can see that this is basically the same thing as our pressure divided by rho, right? Rho equals m divided by v, as you know very well, I'm sure. So this is specific volume. It's just an inversion of density because this is all per mass, right? So if we use that simplification here and assume that for most of our systems we are not really going to have much of an elevation change, that also for control volumes there is no much of a velocity change inside, we assume they are negligible compared to the internal energy and also the pressure work, which is generally, all this is generally a pretty good assumption for control volume analysis. So we can actually simplify this to be the mass flow rate or the total mass flow rate multiplied by the change in enthalpy, right? And that's what gives us the energy state related to the transfer from Q to W, heat to energy. So that difference between the heat and work energy, right? Okay? So now let's talk about that enthalpy. So remember, when you see a capital, like capital U, capital H here, that's when that's a real or base enthalpy or internal energy, real or base enthalpy. When it's a lowercase, like here, that is a specific value. So it's per mass, right? So when you see the lowercase h or the lowercase u, they've been normalized over mass. So like these ones here, right? Oh, previous slide that I just showed here. Okay, so for control volume and control mass, we can get relationships for the change in internal energy. It's all based on specific heats, right? If you have a control volume, you use a specific heat constant. That's what that V here on CV stands for. That's what that V stands for, the bottom. Control volume, you use C sub V. And we know that delta U is just C sub V times your change in temperature. And then for control mass, we can't use C sub V anymore, right? Because it's not constant volume. We need to use C sub P, specific heat constant pressure. Again, so again, this is the definition of where Cp comes from. It's that change in enthalpy but also it is a specific heat constant pressure times the change in temperature, right? So for most liquids, especially if there's only a small temperature change, C sub P and C sub V are almost the same number, and they are approximately equal. So for liquids under small temperature change, they can be approximately the same, so that gamma, which is gamma is Cp C sub P divided by over C sub V, so that equals, that gamma equals 1. But for gases, they can vary widely between each other, and even for small temperature differences, so it doesn't work for gases. So you need to kind of track them through the entire process. You can't assume they are the same for gases, okay? So that ratio Cp over Cv is where you get that gamma, again, that we saw in the diesel cycle, for example, diesel cycle analysis. Remember, it was 1.4, the ideal gas constant. It's the gamma is the heat capacity ratio. We'll come back on that in a minute. So let's talk about a few different processes. We talked about these briefly previously, but when you look at the type of process, look at how that word is formed or how to form the word if you have to define it yourself. And that will tell you what type of process it is, right? So when you see ISO, remember ISO basically means same, it doesn't change, no variation, ISO. For isometric, when you see metric here, that means volume. So isometrics means we have a constant volume process. When we go down here, we get isobaric. So same. So what does baric means? It's like bar. It means same pressure. Isothermal obviously means constant temperature. Then when we get into adiabatic or isentropic processes, that means basically that there is no heat transfer. Important to keep in mind. Adiabatic, no heat transfer. All right. Let's talk about isentropic processes. Adiabatic and isentropic, they work together. It's hand in hand. It's just that isentropic also has the added assumption that the process is also reversible, right? So if you remember from last week, we talked about this a little bit and discussed about reversibility and irreversibility, and how any real system is not reversible. If it's an isentropic process, it means it's adiabatic and that there is no heat transfer going to the outside. Isentropic is necessarily adiabatic. Isentropic is also necessarily reversible. So that means that all the heat is directly converted to work. And because work is the only thing able to come out, that means that the total sum of any change in internal energy and our PDV work equals 0, right here. So maybe you're wondering why, well, they are added together and how do they equal 0? Some of these have to, the response is some of these have to be negative values, right? to equal 0 eventually. And it's probably the heat where you've got negative value. When you add these together, that's how you get the sum total 0, right? So expanded upon that a little bit more, we get this other great idea here of a polytropic process. And what is it? It's an idealized process where basically that's like a rule. It's a polytropic process is where the pressure, volume, temperature obeys the formula PV raised to the power gamma equal constant. PV raised to the power gamma equal constant. This is one of the most fundamental formulas of the whole thermo course. Something to constantly keep in your mind. So what that allows us is to relate one state to another. So state 1, P1, V1, is related to state 2, P2, V2 through that formula. Very convenient. And gamma is the ratio of Cp and Cv. So if we know the pressure and the volume at state 2, at state 1, and we measure the pressure at state 2, as long as we know what gas it is and what that temperature is, we can find out every single parameter here of the transformation of the process. So for gamma, we can look up tables, so get that C sub P or C sub V. We can get the gamma value quite easily. Tables, and each gas has got its own gamma value actually on those tables. So remember, ideal gas law, PV equal nRT. But there is a kind of more simplified non-mass where you get P times V equals RT. P times V equals RT. Basically, it is just ideal gas law. So we can substitute V, that's PV, gamma, PV, PV, gamma, PV, gamma, here you recognize that. So we can substitute for V, and okay, see the gamma here. We can substitute for V in this equation right here, right? So we are just going to, we'll substitute for V on both sides. And so we get a simplification here, canceling out R is disappearing, the gas constant, as long as it's the same gas on both sides, but it should be. Finally, you get this equation down here, solving for T2, and you get T at state 2 equals the temperature at state 1 times the pressure ratio to the gamma here. So now you from all this, you basically have two good tools to calculate what pressures or volumes or temperatures are when you transfer from state 1 to state 2 in ideal gas or air standard analysis. Okay, so I'm going to end this video right now here. In the next one, we are going to quickly talk about this week's lab. Take care.